Magnification calculations for mirrors. So we use two equations, and confusingly, your book uses di and xi, x and d interchangeably. So the equation that's given is the magnification equation, in which the proportion of the image height or the object image height is equal to the negative of the distance that the image is from the mirror over the distance that the object is from the mirror. So the subscript I always refers to the image, and the subscript of O always refers to the object. Now notice that this side is negative, and that's because either you have a real image that is inverted. In that case, the distance of the image would be positive, but the height would be negative, or you have a virtual image that is upright, and in that case, the distance would be negative because it exists behind the mirror, or looks like it exists behind the mirror, but the height is positive. So to reconcile the fact that one of these image or height things is going to be negative, the magnification equation just conveniently makes one of them negative. If the m value is less than 1, that means that the image appears smaller than it actually is. And if the m value is equal to greater than 1, it means that the image appears to be magnified, appears to be larger. And then clearly if the image m is equal to 1, then the image and the actual object seem to be the same height. The next equation looks at the focal distance and the distances. So here x and d are the same, so we're just going to be using 1 over x. 1 over f is equal to 1 over di plus 1 over do. Remember that if you are in a virtual image, then the distance that the image is going to be negative because it looks like it's existing behind the mirror. So some example calculations. I have a 5 centimeter object, that's the height, is placed 10 centimeters from a concave mirror that has a radius of curvature of 16 centimeters. Calculate the di, hi, and m of the object. So these are all of the object, not the image. So the radius of curvature, which is the radius, is going to be equal to 16 centimeters. That's the c, which is twice your focal length, so that'll be 8 centimeters. So I can use the focal length that's given as 8 centimeters and the object distance as 10 centimeters to solve for where the image is. So 1 over 8, 1/8 is equal to 1 over di plus 1/10. In this case, it's easier to convert it to decimals. So you just do that on your calculator by dividing 1 by 8 and 1 by 10, and you get 0.125 is equal to 1 over di plus 0.1. Then you subtract 0.1 from both sides to get 0.025 is equal to 1 over di. It's important not to stop here because what you've solved for is 1 over di, not the di. So you have to flip both. You have to take the reciprocal of both. So the di is equal to 1 over 0.025. And if you plug that into your calculator, you will get that the image appears to be 40 centimeters from the mirror on the positive side. Then I plug this into my calculator in order to figure out my magnification. So if I want to find my magnification is simply 40 over 10 or 4. I'm taking the absolute value here because my magnification is either going to be larger or smaller. The negative sign doesn't mean anything. So when I want to find the height image, I put it into the equation and I first isolate for hi. So hi is equal to di over do times ho. Then I plug my values in and add my units. And I get that my image height, because this is negative here, is negative 20 centimeters, which means that it appears to be upside down. So remember, as a check, one of your values, either di or hi, has to be negative. So it's either in virtual space and upright, or it's in real space and it's inverted. Example B, now I'm looking at a convex mirror. So same 5 centimeter object, still 10 centimeters in front of a convex mirror, same radius of curvature of 16 centimeters, and now I want to see what does that look like in a convex mirror. So it's as if I'm able to turn the mirror around and the shiny side is on the outside. So I have to remember that my focal point and my center of curvature are behind the mirror, and so they will be negative because it exists behind the mirror. So all of a sudden my focal point is negative 8 centimeters. So when I plug it into the equation, I still have the same magnitude of value, 0.125 and zero point 0.1, but this ends up being negative. So when I subtract zero point 0.1 from both sides, I get negative 0.225 is equal to 1 over di. So I take the reciprocal of that, and di is equal to negative 1 over 0.225, and I get an image distance that's negative 4.44 centimeters. It appears to be negative 4.44 centimeters behind the mirror. And if we remember anything about our convex mirrors, we know that our image always appears to be closer than the object. So 4.44 is closer than 10 centimeters. And it always appears to be in virtual space, which means that it has a negative value. Again, when I look at my magnification, I'm really only concerned about the absolute value. So 4.44 over 10, my image appears to be smaller. And that's also something we know about convex mirrors. The convex mirrors will always give us an image that appears to be smaller in height than our actual height. I'm going to verify that by plugging it into this equation, isolating for hi. I plug in my values, and then I solve and add my units, and my height is 2.22 centimeters. The positive value means that it's upright. So again, my di is negative, which means that my hi has to be positive. They both have to have opposite signs, or you've done something wrong. So these are the ways in which the magnification and the focal point distance equations can be used to find quantitative results for the ray diagrams that we draw.